Hello friends, I am Amir Nizami and today we are going to see various types of different loads acting on Abaqus. Okay, so without using the subroutine, how can we make that? So one of my students has asked that if the load is sinusoidal distributed or either it is triangular loading, so how can we make it in Abaqus without using the subroutine? Okay, just like we write a code in a Fortran and we connect with that. So that is the subroutine DF load we can make like that. But that's a complicated thing. Okay, so without using any subroutine, how can we do that? Okay, because this is not directly given. Okay, if you will see the load here, the various load types. So if you want to create a new load, suppose, and then you will see here that the sinusoidal distributed load is not given, okay, anywhere, okay, or the triangular load you can maybe not get directly. So what you will do for that? Okay, so let's see. So if it is a distributed load, it's fine. That's directly given here. Okay, if you will go there, so you are having a magnitude 1 and you get from the pressure. Okay, but let's see what we will do. So let us first write the expression. So if we are having the sinusoidal distributed load, okay, sinusoidal distributed load, okay, distributed load. So how can we make that sinusoidal distributed load? Basically the expression, let's say it's a one-dimensional beam, okay. So if on the beam a sinusoidal load is acting, okay, let's say it's a beam simply supported, let's make it, and the loading is acting here, that is a sinusoidal distributed load. So that may be acting like this. Okay, so this is your sinusoidal distributed load. Okay, so at the mid you can say this is the maximum magnitude acting at amplitude is q naught. Okay, that may be suppose 1 to anything we can take. Okay, so now how to write this in this expression? So basically what is this expression? This expression is nothing but q naught into sine of pi x upon L, okay, where L is the length of the beam, total length of the beam is L, okay. So now if you will see here, so what's the loading here so at this edge the load is 0 and also at this edge the load is 0 and at mid it is maximum of amplitude q naught. Let's see whether it satisfies or not, okay, this equation. So at the rate x equals 0, if you will put 0, q at x 0 would be equals to q naught into sine pi 0. So sine into 0 would be equals to 0. That's satisfying. Okay. So if we say we have taken the coordinate, let's say x uh, equals 0 at this position, and this is the x coordinates at x equal L at this position. Okay. And at the mid x would be L by 2. Yeah. So this distance would be L by 2. So now, so we can say at this edge, sinusoidal load at x equals to 0 would be 0. Now at x equals to L by 2 mid, what would happen? Q at L by 2 would be equals to Q naught into sine of pi, and x equals to what? X equals to L by 2 upon L. So this L would get cancelled. Q naught into sine pi by 2. And we know sine pi by 2 is 1, so q naught into 1 would be equals to q naught. So at that position it would be maximum load. Okay, and similarly if we want to find x equals to L, means at this position what is the loading? So q at x equal L would be q naught into sine of pi L upon L. So this would be q naught into sine pi. Okay, so would be q naught into 0. Sine pi is 0, sine n pi we know, sine of sine function we know that. Okay, from 0 it starts, then again like this. So sine 0 is 0, then sine pi by 2, that is pi by 2, we have one value. Okay, and then at sine pi again 0. Okay, and it would follow like this. So at 3 pi by 2 it would be minus of 1, because we know the range of sine function is -1 to +1. It is -1 to operate +1. and then again 2 pi it would be 0, and so on. Okay, so sin n pi, again 3 pi it would be 0, and 4 pi, and so on. Okay, so that's why sin n pi is 0, so sin pi is 0. So we get this equation at 0, 0, at L by 2 it's 1, okay, that's maximum value, and again at x equals to L it is 0. So this function is satisfying. Let us make this function in this abacus. So let us have this model. So I have copied another model, and I have given it name this sinusoidal load, SDL. Okay, so now let's make this load. Right now it is UDL. Okay, that is in abacus it is called the pressure load. Okay, so how we will make it, let's see. So now we will just edit it. Okay, and this magnitude is given here, or let's do one thing. Let me delete this first, and then we will create a load, and we give the name as SDL load. Okay, SDL, sinusoidal distributed load. So we can't get from here directly the SDL load, sinusoidal distributed load. So we will choose from here pressure. Okay, and then we will go back and go into continue. Okay, and then it's giving the surface to be chosen. So let's say whether we have surface or not itself. So we have the top surface. Okay, if we choose here and highlight the expression, we can see this top surface is chosen. Okay, great. Okay, so we will continue it. Fine. And now what it's asking about the magnitude. We will give the magnitude as 1. Okay, and we will go to this function. Okay, create analytical field. We will create it. We will then have the expression field. Okay, you can see here this is the expression field. We will continue, and now we will write here. So what is the equation? We can see here the equation is our q naught into sin pi x by L. So we have written the value amplitude q naught as 1. Okay, so now what we have to write now? We have to write only sin pi x by L. Okay, so here we have to write this is this in this expression we have to write sin pi x by L. So let's write. So we can get from here sine function. Let's search it. Yeah, we have sine. Okay, so now sine pi, that is pi multiplied by x. Here we can see this expression x divided by L. So what is the length we are having of the beam? So if we didn't remember, okay, what is the length I have chosen? So what we can do? We can go to tools, query, and we can get from here distance. Okay, so to get the distance, we can click on this node, and this node we will get here distance. So you can see here distance is 100. Okay, so what we will do? We will get back. Okay, so let's get back. So we will have the distance as 100. So we will give here 100. Okay, and then we will continue. So we may choose this expression. Okay, so we are applying the load along the y direction. So we will click it, and then finally we will say okay. So this is the load, and what we have to do here, we have to change because it is still showing uniform load. Okay, we don't want uniform load. What we want, we have made analytical field, and if you will say okay, then you may see this is the sinusoidal distributed load. Okay, at this end you can see it's a zero load, no loading is there at this edge, at this point and this point. Okay, left and right. Okay, and then you will see it's moving like this sinusoidal load, and this is at maximum value at the center, and again it's decreasing like this. Okay, so this is the sinusoidal distributed load we are having here. Okay, so now we just dismiss this, and we can run this to see that. Okay, so we will create, and this load job 2 is having sinusoidal distributed load. Let's SDL. Okay, continue. Okay, and then we will just submit the results. Let's see what we get. It is for an homogeneous and isotropic beam. We are seeing these results. So just wait for a few seconds. Let's see. Okay, we got the results, I think. No, not this. Yeah. So you can see these results. Okay. want to see displacements, okay, the magnitude of u1, let's say. So this is of this order, minus 0.5 and 2, so on. Okay, and the transverse displacement, that is u2. You can see this. Okay. This is the order of the displacements. So this is from the sinusoidal distributed load. Okay. If we want other than this sinusoidal distributed load, like triangular loading, okay. So what is the way of triangular loading? What we can do? If we have triangular loading, triangular load like this, so maybe we can get hydrostatic loading there, like that. If there is hydrostatic loading, maybe that would give just like this. So let's see whether in Abaqus itself it's given or not. We'll go to load and we'll just say create load 2. Is there any hydrostatic load somewhere? Concentrated load, moment, shell edge, surface traction. Okay, if it is not showing, we can make it. No, so we can make the triangular loading. Triangular load. Okay. So we'll just continue at the top surface only. Continue. Okay. And okay, so just we can do one thing. We will cancel it. We will model one new copy model, and we will make that as triangular load. Okay, it would be better that a new model is made. Okay, triangular load. It would be much better. Okay, so now we can see in the model we have a new model triangular load. In this we will edit this SDL. We will just either delete it or we can edit it. Okay, so we will rename, or let's say we do delete it. We'll make one new model. We'll give the name triangular load. Okay, and then pressure, that's fine, and top surface, continue. Magnitude, let's keep it 1. Okay, and then we will go to expression. We will write the expression for this, and we will have this analytical field 2. Okay, because initial we have made. So now, okay, now how to write this expression for the triangular load? Let's first do it. Okay, so if we have this triangular loading, this is a linear, yeah. So this is the maximum value, Q0, maximum amplitude here, and this is the total length here, L. Okay, and this is distributed in this manner. So what we can have, how we can get the expression? Let's say we cut any section, let's say 1, 1, at a distance x from here. Okay, so now we know from similar triangle rules, Q0 upon total length is L equal. Okay, now this height, let us say this height, this magnitude is Q1. Okay, so Q1 upon what would be this length now? So total length is L and this is X, L minus X. Okay, so we can write this Q1 in terms of Q1 equal, okay, Q1 would be equal to what? Q0 by L into L minus X. Okay, so now Q0 into L by L would be 1 minus X by L. We can write like this. Okay, so we have the equation Q1 of X. Okay, Q1 of X, that is equals to Q0 into 1 minus X by L. So Q0 into 1 minus X upon L. So this is a function of X itself. Okay, so this Q1 of X is varying. Okay, this may be at any section from 0 to L, in between that. So that's we can write like this. Now let's check whether it satisfies or not. At x equals to 0, it should be maximum value. So Q1 at 0 would be equals to Q0. So how it would be? Q0 into 1 minus x0 by L. So 0 by anything is 0. Okay, so 1 minus 0 is 1. So Q naught into 1 would be Q naught. It's fine. And let's check at Q naught equals to L by 2. So it should be half of that because it's a linear function. So let's check it. Q naught L by 2 would be equals to Q naught into 1 minus x is L by 2 into L. Okay, L would get cancelled, 1 it would be. So Q naught into 1 minus 1 by 2. Okay, so it would be Q naught by 2. So it's fine. If it is a linear function at mid distance, it should be half. And at x equal L, what we will have? At x equal L, it would be Q1 of L would be equals to Q naught into 1 minus x is L, so L by L would be 1. Okay, so Q naught into 1 minus 1, that is 0. Q naught into 0 would be equals to 0. So that is satisfying. Okay, so at x equals to 0, it is maximum, that is Q naught value. At x equals to L by 2, if you come to L by 2, it is half Q naught by 2. So that's fine, it should be half. Okay, and at x equals to L, it should be 0. Okay, so if you match this would be linearly varying. Okay, so my diagram is, sorry, not much good, but it would follow like this. Yeah, so that would be the triangular loading. If we say this is our linear triangular loading. Okay, so we have to write this expression Q naught 1 minus x by L. Okay, or we can write it in a different way, like this also. The expression 1 upon that would be L minus x upon L. Okay, so let us make the L minus x by L. So L is 100 minus, we will take the bracket, and then x. So x is here and divided by 100. Okay, so that would be fine. Then this, we will choose this because it's a vertical loading in that direction. So just complete. So now what we have that, but it is yet showing uniform. We have to choose. So analytical field 2, we have given name. We will say okay. So okay, but yet it's not showing. Why it's not showing the triangular loading? It should show us the triangular load. Let's edit it. Why it's not giving us analytical field 2 1, and if we have this, we have expression 100 minus x by L. That's fine. Then it should give us the correct loading at the top surface. Expression 3, if we make, let's say, okay, analytical, what was the equation? If we see here 1 minus x by L. Okay, so let's make it 1 minus x by L. 1 minus bracket, that is inside, would be x divided by 100. Okay, that's fine. Then we will have this and we will give it, fine. Okay, so now we will give analytical field 3. If say 3, it would be remain 1, and let's say okay, yes. So now we can see here, this is our triangular load. Okay, linearly distributed in this way. So this is our function, and if you run this, let's see whether it's work. Okay, we will create a new job. We'll give the name as triangular loading. Okay, so now continue. Sorry, this here job underscore 3. Yeah, so this is fine. Okay, let's run this, submit it. Okay, I think it's showing the results. Okay, so this would be the results with that, and you may see you making displacements. Okay, so due to this triangular loading, these results are shown. Okay. We may, if we want, we can choose this point and we can draw the displacements, okay, or the any plot if you want the shear stress or the linear stress, okay, sigma axis, we can plot using this. Okay, so for that you may follow my last video, maybe in that I have shown. So I'm closing here. Thank you.